Alright, we're doing episode 9. Again, I'm going to try to go for 1 episode length recording, and no more. Hit 2 last time, so it's better than my worst case, but let's go for 1. Alright, so I wrote all that set-based stuff in the last couple episodes, and I think I got it to a pretty good place, but I actually didn't technically finish it. And what I mean by that is if we come up here, a condition node is actually a set of things, and a condition set is actually a set of things, and so I either want one or both of those to have set operators on them as well. And I'm pretty sure it's just condition set that I want to have set operators, but I'm not sure. So here's where I have all of the subtractors and whatnot for those things. Okay. So I'm gonna just say I want to separate out the stuff that does all this particularly set heavy work so that I can find it easily. Sub recursive set copy. Yeah, there we go. Okay, so let me do this actually so that you can keep track of what file I'm in. I should have done that last time. So I kind of want to do these one more time. I want to do so here I have the thing that constructs conditions, and that's kind of helpful. I want to have the other things as well. I want to know how to subtract 2 conditions from each other and how to intersect 2 conditions from each other, and by conditions I mean condition sets. Right? So we did this math once, but I lost it when we had that disaster in episode 7. So let's just do it again. If I have 2 sets that are made up of these patterns, right, where A and A are the same type, and B are the same type, right, so that it makes sense for these 2 sets to be of the same type as well, these 2 different like set pairs. Then, what is the result there, right? And if I remember correctly, we worked this out to be something like, the idea is you're subtracting out those things which, it's like this, you have we'll do it like this. So the first set is A1, A2, A3, A4. I'll call these C and D to differentiate them from the lowercase letters. So this is A cross B, looks like that. Then if C cross D looks like this, A1, A2, A6, A5, A6, whatever. Point is, when we do that subtraction, the following things would get removed. So you'd lose A1, you'd lose A2, you wouldn't lose A3 or A4, you wouldn't lose B1, you'd lose C1 and C2, right? So it's like you have to represent it as a union of 2 different things. And I'll keep using the shorthand that I established in the last couple episodes. So it's a union, the result is a union of 2 different things. One of those things is all of the things that set A had. So A has letters. A and C are letter types. B and D are numbers. So A has the numbers 1, 3, 4, and 1, 2, 3, and 4, and C does as well. So if I take all of the numbers that A always had, and cross that with all of the letters that B has after you subtract all the letters that D has. So we're going to lose all of the A's and all of the C's. So this would not have A3, A4, C3, or C4 because we're losing all of the letters that D has, no matter what number they have, keeping the rest of the letters and taking everything that A ever had. So 1, 2, 3, and 4 are all present, but only with the letters that aren't eliminated. That's the idea. Then you union that with all of the numbers that were not eliminated, right? So all the numbers that weren't eliminated are no, so intersection would give me the ones that were eliminated. A has all the numbers. I guess it goes like this, A minus C cross with something else. What I want is A and C. Okay, so yeah, that is the... Okay, so this is all letters. A, B, C, D is the set A. Oh wait, I'm doing this the wrong way. So this is all letters A, B, C, D, and those numbers which weren't eliminated, 3 and 4. So this rectangle here is this here, all letters, and 3 and 4, the two numbers that weren't eliminated at all. But that doesn't give me B1, B2, D1, or D2. Okay, I read it wrong earlier. If these are letters, then all of these are kept, but only if the number wasn't destroyed in any location. The 1 and 2 were destroyed, so we don't get these from that expression. So then what we have to do is take all of the letters that B and D, all of the letters that weren't taken out, and cross that with the portion of the numbers that weren't taken out, right? So the letters that weren't taken out are B and D, and I don't want 3s and 4s in there, so I don't want all. I mean, I could just say give me all of those, right? That's the point, is that's actually correct, but it double counts this. So then there's two different ways to not double count that. One way is to say when we take the B set, which is our numbers, and we cross it with the letters that didn't get removed, we also need to make sure we're only adding in the numbers that did get removed. Right, so the numbers that got removed were 1 and 2. And so even though those got removed, they didn't get removed from the letters B and D. So that's why that. Right? The other way to do it is to say, you know what? We did the wrong thing on the first expression. When we added this here, we'll add in all of the B's and all of the D's, because those are the letters that got left over, and we're multiplying by B so that we get all of the numbers. So all the B's are all of the, we get that by taking B times all the numbers, D times all the numbers. B and D are both derived from the things we didn't get removed, never got removed at all. So the things that never got removed are the letters that were in this set that weren't subtracted out by here. That's what we get from this expression, times all the numbers in this set. Good. But I don't want to count any of the letters, right, so this side needs to get A intersect C then, right? In other words, the letters that were affected are A and C, but they weren't affected for the numbers that are left over when you do B minus D. That's the point. So these are the expressions that describe the subtraction, right? And what we want to do is we want to build a set type that is based on A cross B that supports subtraction. So there's our description for that. Now what if we also want to support intersection? Well, in that case, I'm going to add these back in. Take it up here. Here's subtraction. With the results cube being this thing here without any of that, oops, or any of that. Intersection looks like this. It's the set of things that did get removed. So that comes back. That comes back. These go away. Right? So an expression for that doesn't have times signs below anything else. It's okay if it has intersections. We'll figure that part out. Just like this was allowed to have unions. This was allowed to have unions of crosses because we are actually going to build a chain of crosses, and this is what you do if you have two. Okay, I see. So that's the subtraction rule for any two sets, right there. And if they're just basic cross sets, we'll have to figure out what the subtraction rule is for A union B subtract C union D again. We have that up here too, so we've worked that out too. That's going to apply again in a bit. But first, let's work out this intersection here. So that intersection, is that just A int C crossed with B int D? Because that's what it feels like. It really feels like that's all there is to it. Those things which are in A and C are A and C. Those things which are in B and D are 1 and 2. Yeah, that's all it is. So intersection, nice and easy. Union might be the same, I'm not sure. Might not be. So if I take those two and I union them, what would that resulting square look like? It would actually grow. B, C, D. This is actually not trivial. A, B, C, D, E, and F all make it, but 4 and 3 and 4 don't exist in this set, so we didn't actually get this or this. We only got E1, E2, F1, and F2 by adding that in. But we also got A5, A6, didn't get this, C5, C6, didn't get this, E5, E6, and F5, F6. So that's fairly intricate, right? Essentially we have two different things united together. Here's the first thing we had, this, and this all represent three distinct triangles that got, or three distinct rectangles. I mean, we could treat that as one rectangle or treat that as one rectangle, right? But there's like two or three separate sections here that got at least two sections here that can't be merged into one rectangle. Which is good, I guess, because we don't actually have a problem here. This is actually free to represent as just concatenating these things together, because that's what we are actually building. A condition set is a chain of condition nodes. So this is one node, this is one node. A set would just, we would create the union of two of them by just chaining them. So I guess this isn't actually a hard part at all, at least not for the way we're structuring things. So the real question is, can we extend, like, can we see what it looks like when we combine these rules here with unions at the top level? So this is basic subtraction and intersection, but what if we complicate matters? So I want to take a x b union little a x little b. So there's my first set, and subtract, same thing again, but now it's going to be c's and d's. What does that turn into? Well, one step that's always helpful with these set subtractions is to reimagine that this is this, right? That might be a good way to start, because then we can start saying, okay, it's just, how do we push this complement down the chain here? The answer is De Morgan just does it, right? But then how do you push it into there? That is a little bit more tricky. It's not just C inverse of C cross inverse of D. It's actually a union of three things. So let me explain. Suppose I have all the things that are in A, or I'll do C and D. So all the things that are in C, and then over here's all the things that are not in C. Then I have all the things that are in D and all the things that are not in D, right? And so I can build, I have a set called C cross D here, which has only in it those things which are made up of a pair CD, right? So this contains all the pairs that look like this. Well, if I want all the pairs that don't look like that, I want the following things. I want the things that are not in C paired with the things that are not in D. But I also want the things that are in C paired with the things that are not in D, and the things that are not in C paired with the things that are in D. Because none of the things with these forms can be in C cross D, because the things in C cross D can't have anything that wasn't in D. They can't have anything that wasn't in C on the first part, right? So these are actually all included, which makes the complement of a cross, like a multiplication or whatever you want to call it, between two sets, look like this, right? So it's probably unavoidable that sooner or later we're going to have to directly play with that if we keep this up. So let's see if there's a way to go that doesn't go this way, and if we have to, we'll go back to this path. So another option with these things is, as we've seen many times, A union B, when you subtract C union D, what you get is the same as if you took A union, or A minus C union D, and then unions that with everything you get in B minus C union D, right? In other words, you can just take this union and distribute the subtraction over it, right? If you're not convinced by just, you know, a glance, and you were convinced that this path was possible, then let's just distribute over the intersection, right? You agree with me that you can distribute over an intersection, right? So, whoops, I went too far back. We could look at it this way too. To understand, I'm just trying to give you another reason to understand why that would work. So, we were saying combine these as a union and then intersect the result with this. Well, you can always take an intersection and distribute it over a union like that, right? And then we can take these and turn them back into subtractions. Right? So there you go. That is the same as this. So that means if I can answer how do you do this part, I will be there. So instead of answering just this, we'll just say this gets treated as the computation of this by itself, and then the computation of this by itself, and then just chain them together, right? So now, how do we look at just this part? What do we get? Well, this is actually kind of an interesting case. So I think what we want to do is think about the generic case that looks like this. Is that not just the same as saying subtract everything in B and then also subtract everything in C? In other words, couldn't we just say that this is A minus B minus C, right? In other words, if we look at the truth tables for these things, anything that was in A and B won't be in this. Anything that was in A and C won't be in this. Anything that was in A but not in either of these will be in this. So I'm pretty sure that we can just rewrite this as take A cross B and subtract C cross D, and then chain that with another subtraction of the next part, right? So we're kind of going to like shave off one part at a time by shave this off, shave that off, and when we're done, whatever we have left is the new A cross B, right? Now, the only question left then is when we do one of these, what do we get? Well, when we do one of these, we take two nodes and we get back potentially a set. So we can't just say, oh, take two sets and you get a set, because each set is a combination of several nodes, and then those nodes will, when they subtract from each other, create sets again, and those sets will combine back up into a big set. So that's how we have to structure that. But I think this is the right breakdown. Okay, what about intersect? In other words, what about the intersection of unions? The complicated version of that intersection we did up here. So this is a node intersected with a node, but here's a generic set intersected with a generic set. What does that do? Well, classic rewrite strategy is still going to work. We can always take this as, oops, that, and then that separately. So how do we do this part? This is, we can also just do as a redistribution in a non-complicated way. Take out those parentheses there and there. Take out that. Boom, 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 boom. Right, so it turns out that all we're really talking about doing is a thing where we say, for an intersection to work, you take this rectangle, you intersect it with this rectangle, which you then, you have the nodes rule, which is just do that and that. So we intersect A with C and B with D and make a rectangle out of that. And then you do the same thing again with this, and then you do the same thing with this, and the same thing with that and that. So that's also not that complicated. We're just taking every possible pair of these with these. So a nested loop of that and then that. And then for each pair we do this rule. For this one is a little bit more complicated. The rule is separate, for each stage of this, create a copy of the original node and then shave off one of these at each step. And then whatever you have left over, that is the thing that gets contributed on this line, and so then you have a bunch of these sets growing and combining together. Okay? Ready? So we're going to want the following capabilities. Okay, condition node copy. What are some other capabilities I was giving these things? I think it was just copy and then subtract, intersect, union, right? So I need the ability to subtract two nodes. Subtracting two nodes gives me a set. So node A minus node B gives me a new condition set. Node A intersect node A intersect node B gives me another node, which is even tidier, which is nice. And then we won't even bother to have a node level union, but we will have a set level union. As that's just linked list concatenation. And then we also need a set subtract and a set intersect, which get implemented in terms of these node operators that sit underneath them in the hierarchy. Do we need to be able to copy a set? I'm not sure if we do or not. But I'm gonna just say let's better be safe than sorry. So we're going to go ahead and better safe than sorry this particular question, and just say we're going to have an ability to copy a condition set. So there we go. We better safe than sorry that. And then we are halfway through my time. So let's see if I can stick to the plan and just get these implemented before time is up, and call that an episode. One nice self-contained episode. Okay. So a copy of a condition node is just... I should probably do that by pointer. Grab one condition node to return. Fields equals, and then I have field set copy, which I can get by just taking a copy of your fields, and then input set copy to copy the inputs. There we go. Now a condition set's going to be a little bit more work, but not like ridiculously more. It's just a singly nested loop. We've done much worse in constructing the system than that. We've dealt with 4-level loops already, so that's not going to scare us off. And we already have the ability to copy that. arena node, and then we just push it onto the result set. Right? So that's how you copy one of those. Then how do you subtract a node from itself? So this is a little bit more intricate. In fact, this is one of the most interesting and, like, in terms of code-wise, most intricate, like, operation, even though the actual computational cost isn't going to be that high for us. So essentially, we have to determine which of these cases we want to use. This one is not real. That's not like a case we're going to consider, but we want to determine if any of these is preferable to any of the other ones, and doing so is not necessarily easy. So I'm going to just say on a whim that I think subtracting input sets, which would be doing A minus C in my mental model of how this looks. Subtracting input sets gives us the information that we need to know. If that turns out to be empty, then we need to do one of these cases. If it does not turn out to be empty, then we can do either case. Like, we can do, if it's empty, we want to do this essentially by itself. If it's not empty, then what we would do is find out if the intersection is empty, because then we would just do this by itself, and otherwise, okay. So we'll do everything in input set entirely until we're done, and then we'll only do operations on the flags, which are a little bit more scary after. So this goes like this. First, find out what we get when we do A minus B input. SMI input set subtract. Arena A dot inputs B dot inputs. Okay. So if A minus B dot input dot count equals 0, then this is an empty set, and we're going to just go with this case. So then what we do is we need to get a look at if B minus D is something we can easily do. B minus D is field set A minus, so that's an A minus B fields equals SMI field set subtract arena A dot fields B dot fields. If A minus B dot fields field set subtract, how does that indicate an empty set to me ever? I may have made a mistake when I said that I can just always say that the zeroed out one is full, because I need a way to indicate the empty set here. Pin sub right. So when it's doing this, it's basically saying if I don't emit something, right, so scrolling up here to where this is implemented, this is doing this logic here, right, taking the original list, A and B, and then every combination of selections from this, so A, C, or not A, not C, not A, not D, not B, not C, not C, B, not D, and combining those each with this, and then doing the same thing again with this, unioning all that together. So as it's going, anytime it finds that one of these contradicts with one of these, it does not emit it. because like that's an empty set. It doesn't add anything to the union, so we don't emit it into the union. But if it gets to the end and all of it are empty sets, then that means we actually have pin sub result is an empty set. On the other hand, if this and this were both empty sets, then that is indicating, this is weird. So this is actually where it did kind of matter if I figured out whether or not a set was empty or full, which I don't have a way to do. So I kind of need to be able to mark that separately from everything else, because the way it encodes things kind of assumes it's never empty unless I do something specifically. So like the list is clearly empty if it doesn't, or is clearly full if it contains no pins, right? That's the easy part. So a list with nothing in it, yeah. On the other hand, if this has no lists in it, that could mean that it's the full set, or it could mean that it's the empty set. Now I could just say that the full set always has a list that's empty in it. That's what I should do. So this here constructs, okay. Right now that's constructing an empty set, right? Because if there's nothing in it, then it's empty. Because it's a union, and an empty union should be empty. But if I put one list into it, and that list is empty, well that is an empty intersection, and an empty intersection is full. So then I technically have a full set, because I have a union across a list, across a set of sets, but that set of sets only has one set in it, and that one set is full, so the union is full. And the reason the one set inside the set is full is because it is a empty intersection. Does that make sense? I don't know if that makes sense. It's really hard to tell if I'm making any sense to other people, but let's go ahead with this. So the idea is we are going to push a list onto here, but leave it completely empty. So that's it. That's the whole thing. We don't, here we push a list on and then we push a pin on, thus reducing the set to the set of flags that agree with that pin. Here what we're doing is creating a list and putting nothing in it, therefore saying that this set is made up of the union of all these lists, and all these lists starts with one list that has no pins in it, and therefore is completely free to specifies the entire free range of all possible states, right? Hope that makes sense, and not just in the sense that it makes sense to you, but I also hope that it makes sense in the sense that it makes sense in the program, that the code will fit together properly now. So anyway, if we keep going, set subtract, if the thing I get back is an empty set, it'll have no lists in it. If it is a full set, it'll have at least one list that has no pins, or a union of lists that cover the entire space. I mean, if I was really clever, I'd have a thing in the system that says when we union two field sets together, we try to simplify any pins that go in opposite directions by just taking both of them out. That's what I should do. That's not that complicated. So let's see, here what we're doing is we're copying A and B, but what I want to do is not copy B. What I want to do is say, okay, we have A, we're going to stick a copy of A into result, and then we're going to say for everything in B, Now that's more complicated than I thought it was. Let me think this through. So it's not a matter of if they're in the same list, it's a matter of two separate lists have complementary flags, right? But only if those two separate lists with complementary flags agree on the right combination of other flags. Like, it's hard to exactly explain. So if I had one list that was just a 1 in position 1 and another list that was nothing but a 0 in position 1, then between the two of them they could cancel each other out and make just a list with nothing, right? But if they both have complementary bits like that, but they also have complementary bits in the positions for bit 2, for instance, then they can't be combined at all. Because then, yeah, I could say, okay, look, there are two complementary bits. Well, what's happening? Well, remember, the bits pin down, these are pins, so if they point in opposite directions, like one of them says, I pin this to 0, and I pin these first two bits to 0, and the next one says, I pin both of these bits to 1, then they actually both represent sets that when you try to union them together, you wouldn't be able to represent them by simply taking one of those out, because then you'd be saying, if you have, all your bit strings that begin with 0, 0, and a bunch of bit strings that begin with 1, 1, but nothing else, you can't have bit strings that begin with 0, 1, or 1, 0. Yeah. So it would be wrong then to say that that's equivalent to a set where you can have anything in the first position, because you can't. So, never mind. There's a way to simplify, but we're not doing it right now. Which might be a problem. Might lead things to get more complicated than they need to be in terms of how many linked lists there are there, like how many chains of simplifiable information there are, making us do iterations on the order of 4 or 8 when we could have been doing iterations of 1. Anyway, so getting back to just following the script here, and by the script I mean the math right here. A minus B on the fields that's because I determined that A minus C was 0, so I'm doing this case, and so now all I need to do is output one single node. This single new node needs to have its inputs copied from A, and it needs to have its, what is that? Its fields be exactly equal to that thing right there that we've already allocated that isn't going to go anywhere. And then we're done. So that's great, but only if this is not an empty set. If this, which is a union of the things in each list, has no things in there to union, then it's an empty set, and we can just go ahead and return an empty set. No, we can't. No, wait, yes we can. If A minus B is empty and A minus C is empty, then the whole thing is empty. And so Q push result dot first, result dot last, new node, result dot count, 6, 1. Okay. So that's cool. Now what? So we're now in the case where this is non-empty. So I guess the next question is this the full set? Because if this is the full set, which we can check already, then that implies that a int c is an empty set, and we can just do this case by itself, right? So that's what we want to check next. If a minus b dot inputs dot count is equal to a dot inputs dot count. This was an subtraction, right? So since this is a subtraction, if the count hasn't gone down at all, then that means that there was no overlap, and therefore there's no intersection, right? Therefore, this is an empty set, and this can just be a minus b input crossed with that b thing there, which we get from the b by copying the fields out of b. So again, a new node. This time we take the a minus b inputs as the input field, and we field set copy b dot fields and save that. Okay, so we didn't have an empty subtract or a full subtract, so this and this are both not empty. That doesn't actually mean that b minus d isn't going to be empty. B minus d could still be empty. And if it is, then we'll just take this case. So, how do we get b minus d? Well, we've actually done it once already. B minus d is this right here. If a minus b fields count is equal to 0, then that means this is empty, and we already have this computed, and we can get that for free. So we'll use this. We already used this once. That was this code here, right? A minus b that we have sitting right here. Copy of b's fields. We have that right there. It goes right there. Finally, there's the case where we have to combine this with this to get the thing we want, in which case what we get is actually we have to do more than that. We have to do all of these, right? So here we're going to get two nodes. There's going to be like node 1 and there's going to be node 2. So node 1 is A intersect C, right? And its fields are b minus d, which we have sitting right here, a minus b fields. So there we go, there's our first one. The second one needs a minus c, which we have sitting right here, a minus b inputs, and we're going to need a copy of the b fields in that case. There they are. And so the only thing we haven't got is we haven't done the computation for the input set that you get when you do that subtraction, a minus b fields. So let's get that. SMI input set intersect arena a fields, or a inputs b inputs, right? So there's our subtraction of the a inputs of a and the inputs of b. That, and we put that there. No, sorry, not subtraction, the intersection, that, and we put that there. That is the inputs of A, or the fields of A and the fields of D subtracted. That. That is not getting used anywhere. These and this are separate, this and this are separate, so none of these are going to be this, overlapping with anyone else's memory. So there we go. That's the whole description now of how you intersect two of these types of rectangle sets, or not intersect so much as subtract. And the result is that you get 0, 1, or 2 new rectangles. Alright, so how about intersection? Well, intersection of these things is going to be just a doubly nested loop. Oh, the intersection of these is just the intersection of nodes. That's actually almost a trivial case. So the result of the intersection of these, first of all, I want to make sure that, well, I don't see any particularly compelling way to simplify that. So I'm just going to say, this should be a pointer though. So inputs and fields, we just get each of these by doing the intersections of each individual member of the pair. So there we go. There's our intersection. Now we want to do the set subtract. The set subtract differs from the node subtract because the inputs are not two separate rectangles that we need to get subtracted from each other, but two chains of rectangles that are unions together getting subtracted from each other. But that breaks down fairly trivially into just each of the things in the first parameter being handled separately. So let's do a loop over those. So each rectangle in the first chain, give me, and then I want a result right here. Partial. Give me node subset, right? So the idea is I take a node and I subtract the entire set B. And then if partial dot first does not equal 0, then result dot first or result dot last next equals partial dot first, result dot last equals partial last, and result dot count plus equals partial count, right? Implement this one. So we're passing down a node on the left-hand side and a set on the right-hand side, and saying subtract that set from that node. That's what this line represents. So what this line says is that it can be rewritten as a series of subtractions, each one shrinking the original node there. So what we're going to do is say condition node result equals SMI condition node copy. So I have a copy of this node, and then I'm going to say for everything in the set B, we're going to do, and now we get a condition set partial. I'm going to call this node equals, and then I'm going to do condition set. Wait a minute, does this actually return a condition set? Oh yeah, because the subtraction is that. Okay. So I copy that node, and then I set that as the only node in here. Jeez, this is weird. Okay. Okay. So what's going to happen is we've just built this set, but that's not actually going to help, because although that's the type of the result, and we're going to need to take that and subtract a node, That's going to just give us back a set. So we actually need a thing that lets us do set minus node to get a new set. And how would set minus node work? Well, I don't know. Problem is, this is not a full solution after all. Let me think this through a little bit. The reason this isn't a full solution is that, although this is correct, I don't have any obvious way of flowing the data through in a way that I can fully comprehend. I can do a node minus a node, and that gives me a set back. What it gives me back is a set type. Then I can do a breakdown that says that a set minus a set is actually one node minus a set and another node minus a set. And then I can do a breakdown that says this is actually a node minus a node, but then it's that set that comes back as a set, which I then have to subtract another node. You see what I'm saying? So the first one here is a node minus node, but what it gives back is a set, and then I need to be able to answer the question, how do you do a set minus a node to actually keep going? So let's take a look at that part of the problem. How do you do a generic set minus a single node? Is there any obvious tricks? Well, I mean, it's obviously just this, right? So yeah, you can do this. It's just going to mean when we do this first operation, we are basically popping one set one node off the. We're taking a single node set, subtracting a node, and getting out a multi-node set potentially. Then we're iterating each of the nodes there, subtracting them and concatenating them into another set. So yeah, it's going to work. It's just going to be some back and forthiness to it. So this is a good time to use the P1, P2 thing I was doing before. Actually, I can do better than that. All we're doing here is saying for each node in B, result equals, and then do SMI condition set minus node. Here's the arena. Here's the set. Here's the node. Now that raises the question, though, if we're going to have to implement it that way, what if we just, from the beginning, did this all differently, right? What if we said, forget this, this is Loserville. And what we actually want to do is take this concept here and apply it this way. This is this subtracted, followed by this subtracted. We already proved to ourselves satisfactorily that you can do this way. This way we could just take the original set and do this loop right in there, right? Skip having this node subtract set thing entirely. So let's do it that way. We have a set called A, make a hard copy there, loop SMI condition set subtract node, arena result node, and these are the nodes in B now. Then what we do is we take a set and we subtract a node. a minus b. Here we go. Now, how do we do a minus b? That is the easier part. Now that we know how to do this, we're just visiting all the nodes in A. We're doing partial equals condition nodes to do A minus B, and then we're going, alright, if partial has anything to say, then let's take result dot if result dot last does not equal 0, next equals partial first, result dot last equals partial dot last. That's a better structure. If result is empty, then we'll just copy partial right into it. As soon as it stops being empty, we actually have to do the work, but now we don't have to check if result is good, so I like that better. Result count goes up by partial count, right? So we're building up a new result set by combining these partial sets. Each partial set comes as the subtraction of two nodes, and what we get out the other end is the new set you get when you subtract all the nodes in this set from this, and along the way union them back together. That seems fine. And then you set subtract node there to take in this set, and every step of the way you're putting in a new node and getting back another set that's been somewhat reduced. Now, the only thing about this that is a little bit annoying is whenever this doesn't have any effect on A at all, I'm getting back a new copy of A rather than A itself, so that I'm throwing memory up everywhere. Not sure that I care about that stuff. I mean, maybe there's a pass to do over this that looks at reusing these nodes and freeing them or something, but for now I'm happy. I don't want to complicate it, and if we have issues with using too much memory, which is, you know, I mean, geez, but if we do, then we can deal with it. But it's just supposed to be a run once in a while thing, so I don't really care if it needs to spike on memory to do it, to do its job, you know? Okay, we are basically done. The rest of these, I think, work out a little more easily. This is just a loop within a loop. I'm going to try to get this wrapped up within a few minutes so that it counts as a single episode. Okay. So for every node in A and every node in B, intersect those nodes, and if that result is non-empty, stick the result onto a result set. Okay, so that gives me intersection. I see. A node minus B node. Well, intersected B node. Okay, finally unions. Unions are the easiest of all. I believe I've ever done something kind of like this once already, haven't I? Yeah. So, if a dot count does not equal 0, if b dot count does not equal 0, a equals SMI condition set union arena A. Simplify these down. B equals SMI field set SMI condition set union arena B. Result dot first equals A dot. Result dot first equals A dot first. Result dot last equals B dot last. A dot last. Next equals B dot first. Result dot count equals A dot count plus B dot count. Result equals copy A by itself. Copy B by itself. Okay, there we go. So we still haven't finished the transition node problem, the transition optimization problem. But I think for the first time ever we have a pretty good base language for actually approaching the problem. So now, next time we are doing this stuff, we can come back down to this part where I had to if zero out or maybe even delete some of the stuff. No, it was optimize. Yeah, this part. So this part here tries to simplify a transition. Well, actually it tries to simplify all the transitions. And the way it does that is it looks at a transition, it looks at for that transition what is the condition under which this transition takes place, and then what it does is it tries to be more specific and know exactly the answer to that question by looking at previous conditions and subtracting out the set that each of those previous conditions catch, so that what it has left over is just the set that it can actually catch. If that is non-empty, right, this here, then it will continue to it'll keep that as its condition, right? And if not, it'll lose the transfer, or it'll lose the transition entirely. So this basically makes sure we don't have any transitions that are dead weight, that say that they do something that they when they actually don't. This might actually be a good time to say, if we don't want to have to write the simplification code above where we do those things that are like, hey, well, this could actually be simplified, like we have a data structure here that might have redundant information. Maybe this is the place to do that simplification, because you can see we're saying we change the condition for this transition anyway. Maybe this is the time to do that. Just say, hey, here's your real condition. It's been narrowed down to the set of things you can actually potentially get triggered with. And that might have a lot of benefits for us if we do that. So, for instance, when we are trying to optimize out the peaks, we are going to need to have that information, and so instead of having to do this again to find out, just having that stored will be perfect. And it also gives us the perfect opportunity to simplify the sets, which I was saying earlier. So that means I've repeated myself, and the stream can come to an end. Alright, see you later. Bye-bye.